Welcome to this lecture series in group theory. In this lecture, we'll talk about Gauss's lemma. We will prove it in the next lecture, but in this lecture, we'll state it and collect some preparatory material that we will need in order to prove it. So let's recall some basic result. We know from earlier that if P is a prime, then this group Z mod P Z star is cyclic. Here are some problems for practice. These are related problems. You can use this here and this here. And now let's get started. So what is Gauss's theorem? It says, Gauss has proved a lot of theorems, but in this context, in the context of elementary number theory, this is one of his results. If P is an odd prime and n is a positive integer, then this particular group is cyclic. So this is a remarkable generalization of what we just recalled. And this is not true if P equals 2. So this odd prime is important. For P is equal to 2, a similar result is still true. I might state it in the next lecture. So in this lecture, we won't be proving this result, but we will collect the necessary ingredients that we need to prove it. And the next lecture will be devoted to the proof of this. All right, so here is our first lemma. So fix a prime and some positive integer k. Then for any positive integer r, we have this horrible congruence. I can't speak as to what is the meaning of this, but this will be useful. And I have uncreatively called it a useful lemma. So I can't do better than reading it out. It just says that 1 plus k times p to the r whole to the power p is congruent to 1 modulo p to the r plus 1. Let's prove it. The proof is very simple. Just an application of binomial theorem. So we have by binomial theorem that 1 plus kp to the r to the power p is equal to summation I equals 0 to p choose I, k to the I, p to the I r. So I is not the complex number or anything. It's just running over this range. So we have that, and now the first two terms of this series is first term is 1. The second term is p times k to the 1 times p to the r, and the remaining terms are collected here. All right. Now for I greater than equal to 2, p to the ir is divisible by p to the r plus 1, simply because ir exceeds r plus 1 whenever I greater than equal to 2, because r is a positive integer. So therefore this is congruent to 1 plus k times p to the r plus 1 modulo p to the r plus 1, but that is of course congruent to 1 modulo p to the r plus 1. That's it. That proves this lemma. So we will use this in the next. This is our first preparatory lemma. So let p be a prime. Then for any positive integer n, we have this congruence. It looks a little better than the previous one. 1 plus p to the power n plus 1. So this is one integer, horrible one. This is the exponent of this guy. And that is congruent to 1 modulo p to the n. So this is true for all positive integers n. So for n equals 1, this is trivial. Because this becomes 1. For n equals 1, this is 1. So all this is saying is that 1 plus p is congruent to 1 modulo p, which is true. So n equals 1 is trivial, so we will assume n is at least 2. And now what we have is 1 plus p to the power n minus 1. This is equal to 1 plus p to the power n minus 2 to the power p, and that is equal to, so this I need to explain, but let me write it, 1 plus kp to the n minus 1 to the power p for some k. Why is that? So we are using induction on n. Since n is greater than equal to 2, this is greater than equal to 0. Right? So basically n minus 1 is greater than equal to 1. N minus 1 is a positive integer. So we are just using this statement for n replaced by n minus 1. So if you replace n by n minus 1, you get this expression. And instead of p to the n, you get p to the n minus 1. So what this congruence is saying for n replaced by n minus 1 is that this is, or this minus 1 is divisible by this guy. And therefore this is equal to 1 plus some integer times this guy. So this is induction on n. Right, I hope this was clear. Okay. So once we have this, by using the previous lemma, this is congruent to 1 modulo p to the n. So to use the previous lemma, we just need to ensure that this is a positive integer, which it is because n is at least 2. So just by using the previous lemma, this is congruent to 1 modulo p to the n, and that was the statement. That is the statement of this. So just make sure you understand this induction step. The base case of induction is n equals 1. For n greater than equal to 2, we just exploit that this is of, this is one can apply this statement here just by replacing n with n minus 1. All right. So lastly, this is the last preparatory lemma. I think so. So this says that if p is an odd prime and n is at least 2, then this thing. So in the previous slide we had a n minus 1 here, but now we are talking about n minus 2. So 1 plus p to the power p to the n minus 2 is congruent to 1 plus p to the n minus 1 modulo p to the n. So it is not congruent to 1 in particular. Okay, so let's see. Let's do this slowly. So let's first understand for n equals 2. N equals 2, it's trivial, because this becomes 1 and this becomes p. So this is 1 plus, the left hand side is 1 plus p and the right hand side is also 1 plus p, so there's nothing to do. All right, so let's do it for n equals 3. So for n equals 3, we want to show that 1 plus p to the power p is congruent to 1 plus p square modulo p cube. That's what it becomes, but this is just use binomial. So for by binomial theorem, 1 plus p to the power p is equal to 1 plus p times, 1 plus p choose 1 times p plus p choose 2 times p square plus p choose I p I. So all of these are divisible by p. All of these are divisible by p cube, simply because this is divisible by p cube, I being greater than or equal to 3. This is also divisible by p cube because p choose 2 is divisible by p. So I leave that as an exercise. P is an odd prime, and hence p choose 2 is divisible by p. So this part is all divisible by p cube, and hence this is congruent to 1 plus p square modulo p cube. So for n equals 3, we can prove it by hand. All right, let's take a look at n equals 4. So for n equals 4, we are concerned with 1 plus p. Okay, so let me write down the statement. I want to show that 1 plus p to the power p square is congruent to 1 plus p cube modulo p to the power 4. All right, this is what we want to do. But now 1 plus p to the power p square is equal to 1 plus p to the power p to the power p, of course. And now again, we will use the result for n equals 3. So this is equal to 1 plus p square plus kp cube for some k. So here we have used the n equals 3 result. What happened? We know that this is congruent to 1 plus p square, modulo p cube. And therefore this is equal to 1 plus p square plus some multiple of p cube, and that's what we have done. So this is for some k, and I'm not writing that separately. All right, but this is equal to 1 plus p p plus kp square or maybe it's best to just use binomial here. So let's just use binomial theorem. So what we will do is so we will use binomial theorem, but just give me one line. P times p plus kp square to the power p. And now by binomial, what is the first term? It is 1. The second term is p choose 1 times p into p plus kp square. And then all the rest of the terms don't have enough space. Oops. The rest of the terms mean this. P choose I. So this is just p square plus kp square. Sorry, kp cube to the power I. Okay. And since I is greater than or equal to 2 and this much is divisible by p square, therefore this much is divisible by p to the power 4. And hence when we go modulo p to the power 4, this just goes away. So this is congruent to 1 plus p choose 1 is p is p. Then p times kp square is p times 1 plus kp. Yeah, so we should split this further. Okay, so fine. This is congruent to this much modulo p to the power 4. But this is just p cube, so let me write it here itself. And now when p cube is multiplied by p, we get another p to the power 4. So this is congruent to 1 plus p cube plus kp to the power 4 modulo p to the power 4. But since p to the power 4 is divisible by p to the power 4, we can erase it. So I hope you follow the steps. I did not want to take an extra page for this. So basically this induction step is what we will mimic for the general case. This is basically the scheme of the general proof. Here we will have an induction step and then binomial theorem. So let me write it down in one line. So for n greater, basically the general argument would be fix n greater than or equal to 3, or maybe greater than or equal to 4 would be a good idea. Yeah, so let me just be safe and prove it for n greater than or equal to 4, because for n equals 3 we had already done it. So the general argument is 1 plus p to the power n minus 2 is equal to 1 plus p to the power n minus 3 to the power p. Now by induction, this is equal to 1 plus p to the n minus 2 plus k times p to the n minus 1. So this is induction on n. All right. And now binomial. This is 1 plus p choose 1 p to the n minus 2 plus k p to the n minus 1 plus p choose I p to the n minus 2 plus k p to the n minus 1 to the power I. And now you can just proceed. Just like in the previous thing, you just show that this is divisible by p to the power n. And just like here, you just proceed like that. And therefore, ultimately, you will get this is congruent to 1 plus p to the n minus 1 modulo p to the n. Okay. So the takeaway is this. First, we showed, there was a useful lemma. We forget about that. We used it to prove this, which said that if p is a prime and n is a positive integer, then 1 plus p, yeah, so maybe I should say odd prime everywhere. I don't know if this is true for every prime, but yeah, this is certainly true for odd prime. Odd prime, maybe at one point we used the oddness. All right, so let p be an odd prime. Then for any positive integer n, we have this congruence. And for, again, odd prime, just to be safe, p be an odd prime. Then for any integer at least 2, n greater than or equal to 2, we have this thing is not congruent to 1 in particular. This is congruent to 1 plus p to the n minus 1 modulo p to the n, but this is not congruent to 1. So combining this, both of these two together imply, or in fact is equivalent to saying that if p is an odd prime, then the order of this element in this group is that. Because if you raise it to the power that, you get congruent to 1. But if you raise it to the power anything less, anything smaller than this, then you will not get 1. So why is that? First of all, this to the power that is the identity of the group. So whatever is the order of this, that should divide that guy. All right. So if you had a smaller integer dividing this, then it cannot be, it has to be, p to the power something. And if you want to know if, something smaller is the order, then this would also exponentiate to 1, but this does not exponentiate to 1. So nothing smaller than this is the order of, nothing smaller than this can, when this is raised to that exponent, can make it 1. And therefore this is the order of 1 plus p in this group. And this is the fact that we will need to prove Gauss's theorem. So just think about this if you did not get what I was saying, that why is this corollary true? And yeah, with that, I think, forget about that. So with that, I think this is over. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.